Hello all. Gas is a state of matter in which there is a large number of particles of matter which move about inside the container in a random way. That is, different molecules move with different velocities in different direction. However, at a given temperature, we find that there is a particular way the molecules are distributed over various velocities. Often always at a given temperature, we find that a certain fixed number of molecules are traveling with the highest velocity and the other molecules travel with smaller velocity. There is a specific distribution of molecules over various velocity ranges. Certain number of molecules move with certain velocity, certain other number of molecules move with certain other velocity. So there is a distribution of molecules over various velocity ranges. We call this the molecular distribution over the velocity. There is a highest number of molecules moving with a certain velocity. That velocity becomes the most probable velocity. That is, when we observe a certain molecules at random, then most likely it would be found moving with that velocity, which is the most probable one. So here we have a case where different particles are moving with different velocities, and such cases comes under the discipline of statistics. In this video, we shall discuss the statistical distribution of particles over various velocity ranges or various energy states and so on. In case of fundamental particles such as electrons, protons, neutrons, these fundamental particles distribute themselves over specific energy states. That is, they can have this energy state or that energy state but not the energies in between. So these fundamental particles have discrete energy states. Discrete energy states means these energy states can be counted as the first energy, second energy, third energy and so on, because the energies in between are not assumed by fundamental particles. According to classical physics, however, the particles can assume any energy. That is, the energy profile of classical particle forms a continuous band. A classical particle can have any energy, means if we collect all possible energies that a classical particle can have, then those energies form a continuous band as shown in the figure. But in case of fundamental particles such as electrons, protons, neutrons, these particles can occupy only certain energy states under given condition, and therefore if we collect all possible energies that the fundamental particles can assume, then those energies form a discrete state, means there is a gap between the energies and those energies are never occupied. So we say that the energy profile of fundamental particle forms discrete set of energies such as, and this discrete set of energies can be depicted as shown in the figure. This E0 is the smallest energy, it is often called ground state energy state. Then this is the next higher energy state, then next higher energy state E2 and so on. The energies above the ground energy state are called excited energy states. So here we show by this horizontal line the discrete energy states. The energies in between these energy states are not occupied by fundamental particles. So we say that a fundamental particle can have only discrete energy state. But again there is a question, what energy is occupied by what number of particles? If we have a gas of electron, gas of protons or gas of neutrons, then again the gas of this particle behave in some way like the gas of molecules. These fundamental particles have a certain specific way of occupying these discrete energy states. Under given condition, we often find, if you observe the gas of these fundamental particles again and again, most often we find that there is a certain number of fundamental particles in certain energy state, certain other number in certain other energy state. A certain energy state is most populated and that energy state becomes the most probable energy state. And there is a certain highest energy that is occupied by the particle and no higher energies are occupied. So this is the pattern in which the particles occupy various energy state. So this is the statistical distribution of energy state by the particles. So when we have a different number of particles in different energy state, then that case comes under the discipline of statistical mechanics. In statistical mechanics, we try to understand this behavior of particles of distributing themselves in a certain way over different energy state. We try to understand this behavior by the fundamental laws of mechanics which govern the motion of individual particle. The system of gaseous molecule was the first system to be studied in this way. We have laws of thermodynamics which govern the behavior of gases, but the laws of thermodynamics are empirical. We understood those laws of thermodynamics by experiment, but when we use statistical approach, when we use mechanical approach, in a statistical mechanics, we try to understand the laws of thermodynamics in terms of the most basic laws of classical mechanics which govern the motion of individual particles. So statistical mechanics gives us more fundamental way of approaching the problem of motion of gaseous molecules. Now why is it that the classical mechanics says that the particles can have any energy, but these fundamental particles prefer to occupy certain energy states only and not the other? Why is this so? This is because there is a fundamental difference in the way these particles are assumed to be in classical mechanics and the quantum mechanics. It is the quantum mechanical result that they occupy only certain energy states. Classical physics, the picture of particle in quantum mechanics differ from the idea of particle in the classical mechanics. It is that in quantum mechanics, the particle is not a particle, it is a wave. And once we attach this identity to the particle, we can understand why do these fundamental particle occupy only certain energy states and not the other. So the discrete energy state is the natural consequence of quantum mechanics. In this video, we are going to understand how these particles distribute themselves over various energy states. The particle may be a gaseous molecule or an atom, or the particles like electrons, protons, neutrons and photons, and many other fundamental particles. Gaseous molecules have fairly the continuous band of energy, while the other particles, electrons, protons and many other fundamental particles, they possess only discrete set of energies. In this video, however, we shall only consider the discrete case. Moreover, there is a fundamental difference in the way these particles distribute themselves over various energy states. And accordingly, we have three types of distribution: Maxwell-Boltzmann distribution, Fermi-Dirac distribution and Bose-Einstein distribution, which we shall explore in this video. First, we consider Maxwell-Boltzmann distribution. This distribution governs the motion of gaseous molecules. Gaseous molecules do have continuous band of energy, but as I have already said that we shall only consider the case of discrete energy states. Instead of treating directly the gaseous molecules, however, we shall consider a simpler equivalent problem of distribution of balls into boxes. Balls will be the particles and boxes will represent energy state. So distribution of particles over various energy states will be mimicked by the distribution of balls over various boxes. In a system of particles with the constant total energy, certain number of particles are found to occupy certain discrete energy states under given condition. There is a statistical distribution of particles over various energy states. The fundamental assumption of statistical mechanics states that the particle is equally likely to occupy any available energy state subject to the conservation of total energy. The question is, which particle will choose which energy state? So according to the fundamental assumption, a particle is equally likely to occupy any energy state subject to the condition that the total energy of the system of particle must remain constant. So there is no preferred energy state. The distribution of particles over various energy states can be understood using a simpler example of distribution of a given number of balls into a given number of boxes. So let's proceed with ball and box problem. Let's consider 9 balls numbered from 1 to 9 as shown, and the problem is of distributing these balls into 3 boxes as shown. This is box 1, box 2 and box 3, and these vertical bars represent walls of the boxes. The problem is, in how many ways can we distribute these 9 balls into 3 boxes? According to fundamental assumption, any ball is equally likely to occupy any box. So there is no preferred box. We can put any ball in any box with equal probabilities. Instead of considering all the balls together, we start with one ball. We start our distribution with one ball and then take other balls one by one at a time, and accomplish the distribution of all 9 balls into 3 boxes. So we consider one ball first. Let's take the ball number 1. It can go in any of the 3 boxes with equal probability. It may go in box number 1 or box number 2 or box number 3. So we have 3 distinct ways of putting ball 1 into 3 boxes. One ball and 3 boxes. We have 3 distinct arrangements of one ball in 3 boxes. The first arrangement, ball 1 in box 1, second, ball 1 in box 2, ball 1 in box 3. So we have 3 distinct ways of arranging ball 1 in 3 boxes. 3 arrangements for one ball and 3 boxes. Now we take another ball, the ball number 2. Ball number 2, when ball number 1 is box number 1, then ball number 2 is also equally likely to occupy any box. So when ball number 1 is in box number 1, a ball number 2 can be in box number 1, or it can be in box 2, or it can be in box 3. So with ball 1 in box 1, we have 3 distinct arrangements for 2 balls in 3 boxes. This is first, second and third. 3 distinct arrangements for 2 balls in 3 boxes when ball 1 is in box 1. But ball 1 can be in box 2 also, or it can be in box 3 also. And correspondingly, we will have 3 arrangements of 2 balls for each of these 3 arrangements for ball 1 in 3 boxes. So when ball 1 is in box 1, we have 3 distinct arrangements of 2 balls in 3 boxes. So already we have seen these 3 distinct arrangements for 2 balls in 3 boxes when ball 1 is in box 1. When ball 1 is in box 2, again we have 3 distinct arrangements for second ball. Second ball can be in first box, ball 2 can be in second box, and ball 2 in box 3. So with ball 1 in box 2, ball 2 can be in any of the 3 boxes, and again we have 3 different arrangements. When ball 1 is in box 3, again we have 3 distinct arrangements for second ball. So for 3 distinct arrangement of ball 1, 2 and 3, we have 3 distinct arrangement with the second ball. So total number of arrangement, this gives us total number of arrangement of 2 balls in 3 boxes. So total number of arrangement is 3 arrangements 3 times. That is, the total number of arrangements is 3 into 3 equal to 9. Now let's take a third ball and find out the number of ways of arranging 3 balls into 3 boxes. So we have already found that there are 9 distinct ways of arranging 2 balls into 3 boxes. One of the arrangement is having both the balls in the first box as shown. And when both balls are in the first box, the third ball can occupy any of the 3 boxes with equal probability. Here the third ball has occupied box 1. It may occupy box 2 and box 3. So with one of the 9 arrangement of 2 balls in 3 boxes, we have 3 distinct arrangement for 3 balls in 3 boxes. Now here we have shown others of 9 arrangements of 2 balls in 3 boxes. So here we have total 9 arrangement of 2 balls in 3 boxes, and with each of these 9 arrangements we have 3 distinct arrangements for 3 balls in 3 boxes. So with each of these 9 arrangements we have 3 distinct arrangements for 3 balls in 3 boxes. The total number of arrangement of 3 balls in 3 boxes is 9 times 3. That is 3 square into 3, 3 cube and 27. So till now we found the number of ways of distributing 3 balls in 3 boxes, and there are 27 distinct arrangement of 3 balls in 3 boxes. With each of these 27 distinct arrangement of 3 balls, in each of these arrangement, if you bring 4th ball, then 4th ball can occupy any of the 3 boxes. So in each of the 27 arrangement, we have 3 distinct arrangements for 4th balls. So total number of arranging 4 balls into 3 boxes is 27 times 3. That is 3 raised to 4. If we add 5th ball, then with each of 3 raised to 4 arrangement of 4 balls in 3 boxes, if we add 5th ball, if we bring in 5th ball, then we have again 3 distinct arrangement for 5th ball in each of these many arrangements of 4 balls. So for 5 balls into 3 boxes, the total number of arrangements are 3 raised to 4 times 3, that is 3 raised to 5. So if we continue like this, adding more and more balls one at a time, we will find that if we have n balls and m boxes, for example we only consider the case of 3 boxes, if we add nth ball, then the number of arrangements will be 3 raised to n. If instead of 3 boxes we have m boxes, then the number of distinct arrangements of n balls into m boxes will be given by m raised to n. Finally, we have a formula for distribution of n balls into m boxes. Number of arrangements equal m raised to n. We note few points about this kind of distribution. In this distribution, the balls were distinguishable. That is, the balls had their own identity, which we represented by numbering them 1 to 9. And secondly, the balls were equally likely to occupy any boxes. This type of distribution is known as Maxwell-Boltzmann distribution, and this distribution governs the distribution of gaseous molecules over various energies, various velocities. Another type of distribution is Fermi-Dirac distribution. In Fermi-Dirac distribution, the particles behave little different from the case in Maxwell-Boltzmann distribution. In this type of distribution, the particles are indistinguishable with respect to their statistical behavior. In case of Maxwell-Boltzmann distribution, the particles were distinguishable. They had their own identities. which we represented by numbering them as 1 to 9. But in the present case, the balls do not have their distinct identity as far as their statistical behavior is concerned. The balls are indistinguishable. The balls are indistinguishable in that if the two balls exchange their position, then we have no new arrangement because balls are indistinguishable. So this distribution differs from Maxwell-Boltzmann distribution in that the balls are indistinguishable and a box can be occupied by at most one ball. No more than one ball can occupy a box. So box is either empty or occupied by only one ball. No more balls are allowed in a single box. So with these restrictions on the number of balls occupying the boxes, we have to outline the formula for the Fermi-Dirac distribution. So suppose we have m boxes and n balls and they have to be distributed over these m boxes subject to the restriction that at most one ball can occupy a given box. So this is this diagram represents one of the ways we can distribute n balls into m boxes. So the first box have been occupied, then third box is occupied, then this box and this box is occupied. So this is one of the way we can distribute the balls into m boxes. Now if we move the balls from one box to the other box in such a way that there is only the exchange of position of balls, means one occupied box, a ball has been transferred to another occupied box subject to the condition that only one ball is present in a box. So if we move the balls in such a way that the balls have been moved only from one occupied to another occupied box, we get no new arrangement. A new arrangement is obtained only when a ball from occupied box transferred to unoccupied box. So first we consider how we do not get any new arrangement when the balls are moved from one occupied box to another. So here the ball is moved from one occupied box to another occupied box. And see, this is no new arrangement, it is just the arrangement that we previously had. So in spite of the fact that balls have been moved, balls have changed their boxes, we have no new arrangement. This is because the balls are indistinguishable. We cannot make a difference between the two balls. The balls are identical with respect to their behavior of occupying the boxes. So when when a ball from one occupied box is transferred to the next another occupied box, we get no new arrangement. A new arrangement emerges only when a ball from occupied box is transferred to an unoccupied box. So see, the balls have been transferred in such a way that a ball from occupied box is transferred to an unoccupied box. So this arrangement is another distinct arrangement. So balls have to be moved from one box to the other box in such a way that at least one of the unoccupied box must be occupied. Then only we get new arrangement. That is, if we have a certain arrangement of the balls into the boxes, certain specific box are occupied, then new arrangement will be obtained only when we choose another unoccupied box and put a ball into it. So the number of ways in which the balls can be distributed over these m boxes subject to the condition that they are indistinguishable and at most one ball is present in a box. The number of ways of distributing the balls in this way is equal to the number of ways n boxes can be chosen, boxes can be chosen from m boxes. So we only have to choose n out of m boxes and put balls into it, and this will give us one arrangement. Then we choose another set of n boxes from m boxes, another set of n boxes, put the balls into it, it gives us new distinct arrangement. So in the present case, the number of arrangement is equal to the number of ways n boxes can be chosen from m boxes, and this number of ways is given by a combination formula which I have written in this way. We basically write the combination symbol like this, MCN, selecting n boxes out of m, and this is equal to m factorial upon n factorial m minus n factorial. So, the particles which obey Fermi-Dirac distribution, they can occupy m available energy states. N particles can occupy m available energy states in these many ways. The class of particles or the particles which obey Fermi-Dirac distribution in their energy distribution, those particles are called fermions. Electron is one of the examples of such particles. Electrons are fermions. Electrons occupy energy states in this fashion. Once an energy state is quantum energy state is occupied by an electron, no other electron can occupy and company with that electron. A quantum energy state is either occupied by a single electron or unoccupied. Electron is an example of fermions.